Welcome students. In this video we will start with doubly reinforced section. We have already learned what is singly reinforced sections in the previous videos in the previous lectures. So now we will start with doubly reinforced section, and the short form used is DRS. If a beam of specified dimension B by D is required to resist some moment which is greater than MR, that is already derived for a singly reinforced balance section, that is RBD square or RCBD square, then there are two alternatives. One, we have to use an over reinforced section, or we have to use a doubly reinforced section. So if the moment is still MR, that is value MR RBD square, then we can simply design it as a singly reinforced balance section. If it is less than that, again we can go for a singly reinforced section. But if the moment that to be resisted should be more than the value of MR, then we cannot go for a singly reinforced section. It will fail. So either we have to go for over reinforced section or we have to go for a doubly reinforced section. Now, the use of over reinforced section is always uneconomical and unsafe. What is the reason behind this? Main is, see, in over reinforced section we have already learned that the failure is sudden. There are no signs of section cracking or any other failure, but there is a sudden failure when you provide a over reinforced section. So even if it is a singly reinforced section, usually either you can design a balanced section or a under reinforced section, but you usually do not go for over reinforced section, as one, it is uneconomical because you provide extra steel, and it is unsafe because it collapses suddenly. There is no failure that is seen earlier. There is no warning. The other alternative is to provide reinforcement in the compression side of the beam, and thus to increase the moment of resistance of the beam beyond MR for a singly reinforced balance section. So second alternative is you go for a doubly reinforced section. So when I say doubly reinforced section, it means that there is steel in tensile zone as well as there is steel in compression zone. So such sections reinforced with steel in compression and in tension are known as doubly reinforced section, that is DRS. Doubly, from the name itself you will be able to make out the reinforcement is in two sections, two component or two zones. One is tensile zone and another one is compression zone. Okay. Now what is the functions of DRS? When the members are subjected to alternate external loads and bending moment in the section, we have to provide doubly reinforced section, such as concrete piles. You will not understand this why I have given you example of concrete piles right now, but as you study the design concepts, you will get this. So basically, when any structure is loaded or has external loads and bending moment in the section, you have to usually you have to go for a doubly reinforced section. When the members are subjected to eccentric loading on the either side of the axis, such as columns subjected to wind loading. So other than the UDL or the point load in the structure, if there is some external load which is eccentric, it does not act at its center of gravity or it does not act along its axis. Due to external load, there is very high movement that is generated in the structure, and that's the reason we have to go for a doubly reinforced section. Next is when the members are subjected to accidental lateral loads, shock or impact. So at the same time, the moment that will be generated will be more, and for the same reason, we will have to provide doubly reinforced section. Okay. Next is type of beams. So in both the cases, steel reinforcement is provided in tensile zone only. Such beams are called as singly reinforced beams. And if reinforcement is provided in tensile zone and in compression zone to carry compressive stresses, it is known as doubly reinforced section. So the main difference between singly reinforced and doubly reinforced is, in singly reinforced beams, the reinforcement is provided only in the tensile zone, and in doubly reinforced section, reinforcement is provided in tensile as well as compressive zone to carry compressive stresses. What is the working? How does it work? The steel reinforcement provided in compression zone is subjected to compressive stress. Okay, in singly reinforced, what happened? The steel that is provided in tensile zone is subjected to tensile stress. Now here the steel that is provided in the compression zone is subjected to compressive stresses because there will be only compression in that particular area. However, concrete undergoes creep strain due to continued compressive stresses. Creep is long term. So, because of these compressive stresses, the concrete undergoes long-term strain. Thus, the strain in concrete goes on increasing with time. So, as the time increases, the strain also increases in compression zone. This increases the compressive strain in the compressive steel in addition to creep strain. So, see, first what happens? Due to the compressive stress, there is long-term strain that is generated in the concrete. Due to this long-term strain in the concrete, there is increase in compression strain in compressive steel. So, like it increases in concrete, it increases in steel also, in addition to creep strain. So, thus the total compressive strain in compressive steel will be much greater than the strain in surrounding concrete due to flexure alone. So, the strain that is generated in concrete only is much lesser as compared to the compressive strain that is developed in compressive steel. Okay, so in total it is more as compared to the strain in concrete. Now, what does IS 456 say? According to the IS, the compressive stress in steel should be calculated by multiplying the stress in the surrounding concrete by 1.5 times M. That is, modular ratio for steel in compression zone is 1.5 times the modular ratio that is normally used. So if in singly reinforced section modular ratio is M, just a value M, here it is denoted as MC and it is equal to 1.5 times M. So it is more. Okay. So modular ratio that is considered is more. This is the stress and strain diagram for a doubly reinforced section and this is how it is going to look. So if you see, this is a rectangular section. There is AST, that is amount of steel that is provided in tensile zone, and there is steel that is provided in compression zone, and this is named as ASC. Okay, this is the width of the section. This is the depth of neutral axis N, that remains the same. This is the effective depth of the structure beam, that is small d, and this is DC, that is the distance from the top compressive fiber till the center of the reinforcement in compression zone, which is again taken as E times D, where E is the constant. Like we had taken N is equal to K times D, or the lever arm was A is equal to J times D. Here it is taken as E times D. Now, if you see the stress diagram, the stress at this point increases. Similarly, the tensile stress is T by M. Okay, now at this point, like how we have tensile stress here at the center of tensile steel, similarly we will have stress at the point where compressive steel is provided. So it is named as C dash. This is T by M at steel in tensile. This is C dash at the steel in compression. So C dash is equal to TC upon MC. We will understand this when we do the derivation. So for now you have to just know that there is a compressive stress in the compressive steel, that is C dash. Similarly, the strain diagram, if you see, there will be tensile force capital T, which is divided into two parts, that is T1 and T2. Also, you will understand this what is T1 and T2 with the derivation. Now, there are two compressive forces here. One is C1 and other one is C2. C1 is the compressive force that is generated due to the compression stress in concrete. And C2 is the compressive force that is generated in the compressive steel. Like we have T in tensile steel, we have C2 in compression steel. And C1 is the value C that we had in singly reinforced section. It was only one compressive force that time. It was due to the concrete that is there in compression zone. So that is equal to C1 here. And C2 is an additional compressive force that is acting at the compressive steel. So moving ahead, the depth of neutral axis can be found by finding the center of gravity of the combined section consisting of concrete in compression only and steel in compression and tension. So how we have to find out the neutral axis? Basically, again, if we have to design the section, we have to find out the depth of neutral axis or position of the neutral axis, so that we divide the section into two zones. One is tensile zone and compression zone, and then we design it accordingly. So let B be the width of the beam, D is the effective depth of the beam, DC is depth of center of compressive steel, which is equal to E times T. I've already explained to you all this in the diagram. E is the compressive steel depth factor. Physically, it is a constant. Small c is maximum stress in steel concrete. T is maximum stress in steel. These are the same things which we use in singly reinforced section. C dash, this is an extra quantity which is stress in concrete surrounding compressive steel. Tc is stress in compressive steel, which is equal to mc into c dash, and mc is equal to 1.5 times m, that is a 1.5 times normal modular ratio. AST is area of steel in tension. ASC is area of steel in compression. MC is modular ratio of compression zone, which is equal to 1.5 times M. This we have already explained. So here the extra things that we need to take care is DC, E, C dash, TC and ASC, and also MC. Okay, all the other things are same as what we have learned in singly reinforced section. So using the stress diagram, we will do a derivation to find out the depth of neutral axis in the next video. Thank you.